Good morning, class. We are looking at chapter 2, review, which is limits and derivatives. So in this chapter, we cover the tangential velocity problems, the limit of a function, calculating limits using the limit laws, the precise definition, continuity, limits at infinity, horizontal asymptotes, derivatives and rates of change, the derivatives as a function. So we looked at the concept of a limit, and the idea is we are interested in finding a value near an x value, and then what is the value along the y-axis. That's called the limit. We may not ever get to a, so that's why the limit of f of x as x approaches a. As you can see in all of these graphs is L, but in the first case, f of a is also L, which is the definition of a continuity, but f of a in part B is a different value, which makes it discontinuous at A. And in part C, f of a is not even given because we don't have a solid point. And that gives us the concept of a one-sided limit. The limit from the left and right must be identical for the limit to exist. Then in this example, we looked at the concept from the point of view of numerical, graphical, and algebraic method. Numerical, from the left, we get closer and closer to the value of interest. In this case, is 1. From the right, and then we observe the y value, which becomes the concept of a limit. The graph gives us the same thing, an algebraic method, which in this case requires factoring. The concept of a direct substitution when we are dealing with continuous functions, and also the squeeze theorem. If G is between f and h, and the limit of f and h, both of them as x approaches a is the same thing, then the limit of the G must also be. Right here, again, the discussion was about limit from the left and right, and approaching number 2 from the left and right, number 4 from the left and right. Number 2 doesn't have a limit, number 4 does, and it's a one-sided limit. We got to be careful. When the limit ends up being infinity or negative infinity, it gives rise to what we call VA, vertical asymptotes, and in this case, there are 3 of those. And ultimately, to find the limits, the best course of action would be to plug in and observe. When we get to a number, we are done. 0 over a number is 0. A number over 0, we have to figure out positive or negative. And in many cases in calculus, we end up with indeterminate forms, meaning 0 over 0, infinity over infinity, infinity minus infinity, and there are other forms. In both cases here, if you look at part A, in this case, it's 0 over 0, and the technique is the conjugate of the numerator. You multiply and divide by the conjugate of the numerator, and it gives you an answer. In both cases, B and C, the numerator is -1 and the denominator is 0. However, the one-sided limit gives us the first case 0 from the right, and negative over positive ends up being negative, which means negative infinity. In this case, negative over negative results in positive infinity. In part A, we just plug in and we end up with 0 over 0, and the technique is factoring. Since x approaches 4, we should have a factor of x minus 4. We do, and we end up with 4 over 5. In part B, 0 over 0, the technique is to multiply and divide by the conjugate to come up with the answer. In part A, we plug in and it works out. In part B, we get 0 over 0, and the technique is to multiply by LCD because it is a complex fraction. We want to evaluate the limits, again, understanding the graphs, being able to read the limit from the left and right, whether they exist or not, and using the limit laws, and the combination of all of those will result in the answer. We've gone over this question with details. And the concept of a squeeze theorem, I want to make sure everybody understands. Again, for part A, we looked at 2x, and we took the limit as x approaches 1. We looked at the right side, the x to the power of 4 minus x squared plus 2. We took the limit as x approaches 1. And since both of them give us number 2, then G must have the same limit as x approaches 1. In this case, there is a trick involved. This one is pretty involved. So we know that sign is between -1 and 1. So it doesn't matter sign of alpha, whatever the argument may be, sign of alpha or sign of 2 pi over x makes no differences between -1 and 1. So when we raise it to the second power, of course, 1 squared becomes 1, but it is important to know if you have a negative number, it ends up being 0 because any negative number ends up being positive. So you have to go from 0. We go through the process and we add, we square this, we add 1, and then we multiply by square root of x. And you want to be careful anytime you're dealing with inequalities, because multiplication by a negative number will flip over everything, and it ends up being 0 by the squeeze theorem again. In this case, we use a one-sided limit, and there are a couple of approaches. First, understanding the absolute value of x means it's x if x is positive or 0, and it's minus x otherwise if it's less than 0. And if you understand this concept, that means if we have an expression, we drop the absolute value if that expression is positive or 0 and negative of that. And so using that methodology, the limit from the left of -6 being -2, from the right being 2, means the limit does not exist. So that's what we've done so far, and we're going to move on to the new stuff. The precise definition. So the limit of f of x as x approaches 3 equals 5, as an example. What does it mean? It means f of x is close to 5. That means the y value is close to 5 when x is close to 3. So the y value is close to 5. It's in the vicinity of 5, where the x value is close to 3, in the vicinity of 3, meaning it never gets to 3. We are not interested in what happens at x equals 3. In fact, x is not equal to 3. So the formal definition, and using mathematical symbols, this is read: whatever epsilon larger than 0 there exists delta larger than 0, such that if the absolute value of x minus a is less than delta, that means then that absolute value of f of x minus l is less than epsilon. So I write this, and then I need this space. I'm going to erase it. This means, this symbol means whatever. Okay, this symbol means there exists, and this sort of vertical line segment is read such that. So let me quickly go over it one more time. Whatever the value of epsilon larger than 0, there is a delta larger than 0. Both epsilon and delta are extremely small numbers, such that if the absolute value of x minus a is less than delta, that means the distance, remember the absolute value refers to distance, the distance between x and a is extremely small, delta value. Then the absolute value of f of x minus L, that means the distance between the functional value and the limit is less than epsilon. I have to erase those. I will do them in a moment. So what does it mean in this example? We can make the values of f of x within an arbitrary distance epsilon from 5 by restricting the values of x to be within distance delta from 3, but x cannot be equal to 3. In other words, if x is between 3 minus delta and 3 plus delta, that has got to do with this absolute value, then 5 minus epsilon is less than f of x, less than 5 plus epsilon. Again, this has got to do with this absolute value and the concept of that. I will write it down in a moment. By taking the values of x not equal to 3 to lie in the interval of 3 minus delta and 3 plus delta, we can make the values of f of x lie in the interval of 5 minus epsilon, 5 plus epsilon. It's important to understand when we are looking at this one, for example, it means x minus a. If you want to drop the absolute value, you put minus delta and plus delta. I hope you remember from elementary algebra, if this is less than a, assuming a is positive, then we can say it's sandwiched between negative and positive a. And so that's exactly what we are doing, and we're moving the a, so it becomes a minus delta less than x less than a plus delta. And that's exactly what this gives us, and it works out the same way here. So refreshing everyone's memory about the meaning of absolute value of x less than a. When a is positive, you can drop the absolute value and put it between negative and positive a. It's an intersection of events. This is a compound inequality. Minus a is less than x and x is less than a. That's the meaning. We need this space. Let's erase up. And so precise definition of limits, let f of x be a function defined on some open interval that contains a except possibly at a itself. We say that the function has a limit at a, and we write limit of f of x as x approaches a equals L if for every small number epsilon larger than 0, there is a number delta larger than 0. Again, that's a very small number, such that if the absolute value of x minus a is less than delta, normally we say larger than 0. Absolute value is anyways a positive, worst case scenario is 0. So this is given in essence. Then the absolute value of f of x minus L is less than epsilon. So that's a precise definition. And so let's look at quickly a couple of examples. And so what happens is that along the x-axis, the value is somewhere between a minus delta and a plus delta, and a is smacked in between, and it maps it to the y-axis between L minus epsilon and L plus epsilon, where L is right here, smacked in between. So that's how it maps it. So we're going to use this graph to find delta such that if absolute value of x minus 3 is between 0 and delta, absolute value of f of x minus 2 is less than 0.5. And so first and foremost, I like to have this always, whatever epsilon larger than 0, there is delta larger than 0, such that if absolute value of x minus a is less than delta, then the absolute value of f of x minus L less than epsilon. In general, the concept is this, the concept. Guessing a value for delta given epsilon larger than 0, we need to find or guess delta such that if the absolute value of x minus a is between 0 and delta, then f of x minus L, the absolute value is less than epsilon. That's the concept. So we always start with this one. And so that means we start with this one. This is what's given. Absolute value of f of x minus 2 less than 0.5. And then I went over the concept of an absolute value. This means you can drop the absolute value, put it between negative and positive 0.5. Now we're going to add 2 to all sides. And f of x is between 1.5 and 2.5 as it is indicated in the graph anyways. Now, if we look at the graph, we notice from the graph, x is somewhere between 2.6 and 3.8 from the graph. So what do we take? We take delta to be the minimum of those two distances, meaning 3 minus 2.6 and 3.8 minus 3. I want you to look at this. This is the distance between these two. This is the distance between these two. And we always take the smaller of the two to be on the safe side. And so the distance between these two is 0.4. Between these two is 0.8. So everybody can see that this one is 3 minus 2.6. So this is 3 minus 2.6. And this is 3.8 minus 3. So it's between 0.4 and 0.8. And the smaller of the two is 0.4. So we take 0.4 to be the answer. Why is that? If you take the larger of the two, this side is fine. But this side, if we go by 0.8 to the left of 3, we end up with 2.2, and it's beyond 1.5 to 2.5. So you should always get the smaller of the two. And needless to say, any smaller number than 0.4 will do the job. So you were trying to find this from the graph. In short, basically the smaller of the two is the answer. And any number less than that. We just want to go over that and make sure the concept is understood. But in short, we go between 1.5 and 2.5 along the y-axis. We go between 2.6 and 3.8 along the x-axis, and the smaller of the two distances is the answer for this question. Again, I like to have this written, this concept. Here's the question. We want to prove the limit of 4x minus 5x as x approaches 3 equals 7. As you recall, we normally plug in, and if it gives us an answer, we are done. In this case, 4 times 312 minus 5 equals 7. But proving it, precise definition has a specific methodology. So there is a write out using this. So here's the methodology. So you write this. If the absolute value of x minus a is less than delta, that means the absolute value of f of x minus L must be less than epsilon. So when we look at this one, I hope you realize that a is 3, f of x is 4x minus 5, and the limit is 7. So we write this, and from here, we replace what we must. So again, a is 3, The function is 4x minus 5. The limit is 7. And so we always start from this one and we go to this one and we find a relationship between epsilon and delta. That's the precise proof. So your job is to find a relationship between these two. So that's why we always start with this. We start with this. So the absolute value of 4x minus 5 minus 7 less than epsilon. And of course, that will give us minus 12. And our job really ultimately is to make sure we get this factor somehow here. And you may notice that over here, I can take the 4 out. And pretty much you see what's happening here. So this is the same as this one with a factor of 4. So I can divide this by 4 because I want it to look like this. If I divide this by 4, then the absolute value of x minus 3 is less than epsilon over 4. So we got this on the one hand. On the other hand, we know this. So let's put them next to each other. So we're going to compare what we have now to this. This is what we ended up with. Let's compare it to this one. So what does it mean? Choose delta to be 1/4 of epsilon. This means the choice must be delta is epsilon divided by 4. And that's really the main part, understanding how we come up, going through the process, coming up with a relationship between the two, epsilon and delta. Now, as far as the proof is concerned, is the reverse steps. So proof showing that this delta works, reverse steps. And so we start with this. This is where we start. And we go back. That's the concept. So we know the absolute value of x minus 3 is less than delta, and we've chosen it to be epsilon over 4. Let's multiply both sides by 4. We are interested in this one. This is not that important, everybody. So for delta or epsilon. Now, what is our job? Our job is to make this look like this one that we got, or this one. We want to make it look like this one. So we can take the 4 in. So it's the reverse process. We're going to take the 4 in. 4x minus 12. Take a look. 4x minus 12. And we know we can write it as 4x minus 5 minus 7. So remember, it's a reverse process. So we're going to make this 4x minus 5 minus 7, the reverse process. And so, what does it mean? When we put these two together, from the definition here or here, if this, then that. So if the absolute value of x minus 3 is less than delta, then the absolute value of 4x minus 5 minus 7 is less than epsilon, and that's the precise definition of a limit. That means, therefore, this works, and the limit of 4x minus 5 as x approaches 3 equals 7. If we were to go with the graph, we can look at the graph of the function y or f of x equals 4x minus 5, and here's 3. We go by sigma, by delta to the left and right of it, and at top, this is 7. We go up and down by epsilon from 7. That's how it looks like. So within delta of 3, we get the answer within epsilon and 7. And by the way, it is important to know that both numbers are extremely small. But this is the precise definition of limit. Let's go to continuity. In essence, we've already discussed that. A function has a limit at a if the limit of f of x as x approaches a from the left equals L, and that is equal to the limit of f of x as x approaches a from the right, meaning the limit exists. The limit of f of x as x approaches a equals L. Direct substitution property. For polynomials or rational numbers, if the function exists at the value a, then the limit of the function as x approaches c is equal to the function's value at a. In other words, the limit of f of x as x approaches a equals f of a. What they're saying is that certain functions, we know they are continuous, but in general, I'm going to claim that every function that we have studied, they're all continuous in their domain, and that's really the key. So let me write this. All functions are continuous in their domain. Everything that we have studied. For example, even a rational function, you have to know what is the domain. The domain is all real numbers except what makes the denominator 0. So you can exclude that, and then it's continuous in its entire domain. I need a space. A function is continuous if the limit of f of x as x approaches a equals f of a. So in essence, there are three conditions. The limit of f of x as x approaches a from the left must be L. The limit of f of x as x approaches a from the right must be L, which makes the two are identical, and it must be equal to the functional value. So a function is continuous from the right if the limit of f of x as x approaches a from the right is f of a, and it's continuous from the left if the limit of f of x as x approaches a from the left is f of a. So when the function is discontinuous, it is possible that it's continuous from one side as long as the limit of that side is equal to f of a. And also let's add the IVT. We had seen this previously in pre-calculus and college algebra. If f of x is a continuous function on the closed interval of a to b, and let n be any number between f of a and f of b where the two values are not equal, there must exist a number c in a b such that f of c equals n. So the bottom line is, if we have a continuous function, every point of this function must be covered along the x-axis as well as along the y-axis. That's all it says. Therefore, the IVT, the intermediate value theorem, applies. So if you happen to have a piece that is continuous from A to B, and assuming f of A, for example, is less than f of B, so any number in between must be covered along the y-axis. We want to determine C such that this function is continuous at x equals 5, which means we have to follow that. First and foremost, we need to take the limit of this function. So to take the limit, it's a piecewise defined function. The top piece says x cannot be 5. So this is the piece you use to take a limit. And I hope you notice if you plug in, you get 0 over 0. So the technique is factoring, and obviously you see the factor of x minus 5 is already down here, and the top is a squared minus b squared. So it's x minus 5x plus 5. So we can drop a common factor of x minus 5. And when we plug in, we get to 10. So how do we make sure this is a continuous function? According to this, P of 5 is C. So if we have the limit to be 10, then the P of 5, which is C, must be equal to that. C must be 10. So the limit of P of x as x approaches 5, must be equal to P of 5, and we know this one to be C. So setting this to equal makes C equals 10. Show the function is continuous from negative to positive infinity. F of x is sine x if x is less than pi over 4, and cosine x if x is larger than or equal to pi over 4. Now, how do we check that all sinusoidal functions are continuous from negative to positive infinity? Sine is continuous from negative to positive infinity. You know the domain of sine. So is cosine. So each piece is continuous in their entire domain. So this one is continuous from 0 to pi over 4, and this one is continuous from pi over 4 to infinity, because it's defined for the sine to be less than pi over 4, for the cosine to be larger than or equal to pi over 4. So we know by this, f is continuous from negative infinity to pi over 4 union pi over 4 to infinity. The only thing we need to check is the end point, namely pi over 4. And it happens with piecewise defined functions that it's mostly the end piece that we have to check, the end point. So what we need to do, we are going to take a look at the function and take a limit as it approaches pi over 4 from the left, pi over 4 from the right, and f of pi over 4. We're going to look at those three things. So we're going to do this, but we're going to do it with one-sided limit. So the limit of f of x as x approaches pi over 4 from the left uses this piece of the function. So the limit of sine x as x approaches pi over 4 from the left. And so basically we can plug in its sine of pi over 4. And you know it to be square root of 2 over 2. I'm assuming we are okay with basic trigonometry. So that's the left-sided limit. The right-sided limit, we're going to do the same thing, but pi over 4 from the right. So pi over 4 from the right, we use the second piece, cosine x. So the limit of f of x as x approaches pi over 4 from the right uses the second piece, the limit of cosine x as x approaches pi over 4 from the right, which means cosine of pi over 4, and that is also square root of 2 over 2. So the limit from the left, the limit from the right, they're identical. So the limit exists. And as far as the functional value is concerned, you have to look at the pieces, and the one with the equality is the functional value. So f of pi over 4 will use the second piece, cosine x. So it becomes cosine of pi over 4, which is also square root of 2 over 2. So again, why are we using this for the functional value? Because of the equality. So the limit of f of x as x approaches pi over 4 and f of pi over 4, they are identical, square root of 2 over 2. And that means it is continuous at pi over 4. So when we go back to this, it was continuous everywhere. We didn't know about pi over 4. We checked it. And therefore, because we proved it is continuous at pi over 4 in conjunction with this one, f is continuous, CTS short for continuous, on negative to positive infinity. So a quick recap. Sine and cosine, they are both continuous from negative to positive infinity. The limitation from the piecewise defined function makes sine continuous from negative infinity to pi over 4, cosine from pi over 4 to infinity. And so this is the answer, and the endpoint pi over 4 must be checked. We just checked it. Use the intermediate value theorem to show there is a root for this equation sine x equals x squared minus x between 2 and 3. So again, reminding everyone, the intermediate value theorem says if f of x is a continuous function on the closed interval of a to b, and let n be any number in between f of a and f of b, where the two values are not equal, there must exist a number c in a and b such that f of c equals n. So this concept, again, if we were to illustrate that, I want to make sure we understand. So if we have, let's say this is the function, this is a, this is b. I want to make sure that we understand the concept. So this is f of a, this is f of b. So if we have a number in between, a number between this, let's say this is n, then because n is between f of a and f of b, assuming f of b is larger, then because it's continuous, it cuts it somewhere here. So there must be a c such that now this equals f of c. That's what this IVT stands for. All right. So I wanted to do the illustration, so making sure everybody understands the concept graphically may make it easier to understand. Let's erase so we can use the space. We're going to bring everything to one side. It doesn't matter left or right. And we're going to call that f of x. And this function is continuous because it's a mixture of a, you can say polynomial or even a quadratic function and a sine function, and each one is continuous from negative to positive infinity. So the reason it's continuous because it's the sum of QF quadratic function and sine function. Remember, minus sign, subtraction is a form of addition. That's why we call it the sum of a quadratic function. X squared minus x is a quadratic function, and a sine function. One might say, well, this is a linear function, but you can look at this combination as a quadratic function, or you can even say quadratic, linear, and sine. In any event, so at this point, finding the solution for this equation is not easy, and it's done by inspection. So for example, if we plug in 1, we get to a negative value. Let me make sure everybody understands why. And if we plug in 2, we get a positive value. So I'll show you both cases. So f of 1. So if I plug in 1 here, I get 1 squared minus 1 minus sine 1. And that is minus sine 1. By 1, we mean 1 radian. And that is negative. If I plug in 2, I get 2 squared minus 2 minus sine 2. Now 2 squared is 4, 4 minus 2 is 2, so 2 minus sine 2. You don't even have to know what sine 2 to know this is positive. Why is it? Because you know sine is between -1 and 1. In the worst case, it's 1, so 2 minus 1 makes it still positive 1. Okay. So I hope you realize why this is positive. So one of them is negative, one of them is positive, 0 is in between. So IVT, the intermediate value theorem, applies. F of x is continuous on 2 and 3, on the interval of 2 and 3, and has a root in between, because that's what it means. That means there is f of x. The meaning of this is some functional value equal to 0. That means a root. Or if you're looking at the graph, it's called the x-intercept. The root refers to an x-intercept. Limits of functions at infinity, horizontal asymptotes. If we take a limit of a function when x approaches negative infinity and it gives us a value L, or if we take a limit of f of x as x approaches infinity, it gives us L. Either way, we have a horizontal asymptote of the equation y equals L. This is the definition. Other things that we want to quickly remind everybody, the limit of 1 over x as x approaches infinity is 0, simply because what this says, when you have a fraction, as the denominator gets larger and larger, the fraction gets closer and closer to 0. The same thing here, 1 over x to the power of p. The limit of 1 over x to the power of p as x approaches infinity is 0 when p is larger than 0. And this is important to know why p is larger than 0, because if it's negative, it can come up. Remember, it has got to do with the exponential rules. All right, let's look at this function, an exponential function. This one is an exponential growth when the base is larger than 1. This is an exponential decay when the base is between 0 and 1. So, for example, e to the power of x looks like this. So the limit of e to the power of x as x approaches minus infinity is 0, which means in this case y equals 0. The x-axis is the horizontal asymptote. The limit of f of x as x approaches infinity is infinity. And you really need to know, and I hope you remember, this stuff refers to what we call the end behavior of a function. This is also known in algebra when we were graphing. The end behavior. We have behavior near an x-intercept. We have the end behavior. And so for the exponential decay, the limit of e to the power minus x, as an example, as x approaches infinity is 0. Again, of course, gives us the horizontal asymptote, y equals 0, and the limit of f of x as x approaches minus infinity is infinity, the end behavior. Another end behavior dealing with y equals x cubed, reminding everyone the graph looks like this, and it's important to know the graph of all essential functions, elementary functions. So we should easily answer this, and therefore the limit of f of x as x approaches minus infinity is minus infinity. This is referring to the third quadrant, and the limit of f of x as x approaches infinity is infinity. That's referring to the first quadrant. Again, the end behavior. Definition of a vertical asymptote: when we take a limit of f of x as x approaches a, whether it's a or a from the left or a from the right makes no difference. If it ends up being positive or negative infinity, then we have a vertical VA, vertical asymptote x equals a. That's by definition. So for example, one of those functions that we know the graph y equals logarithmic functions, for example, y equals ln x. And as you can see, the limit of this function as x approaches 0 from the right is minus infinity. Remember, the domain is 0 to infinity, and it's not defined when it's negative or it's 0. And this gives rise to VA, vertical asymptote, having equation x equals 0. And so definition of a vertical asymptote of the curve y equals f of x is x equals a. So we can rewrite this as the limit of f of x as x approaches a is plus minus infinity. Limit of f of x as x approaches a from the left is plus minus infinity, or from the right. The same thing I'm repeating in essence, and reminding you of the horizontal asymptote in the case of this function, because normally we don't have more than one horizontal asymptote. In this case, we do. This is the tan inverse. The limit of tan inverse as x approaches minus infinity is minus pi over 2, and the limit of tan inverse of x as x approaches infinity is pi over 2. And again, perhaps this will help to remind you. This is y equals tan x. So it looks like this, and it goes from x equals minus pi over 2 to x equals pi over 2 when we want a complete cycle. That's what we do. So just to refresh your memory about some of this stuff, and now we are going to work on some examples. We want to take a limit of 5t plus 7 over t squared plus 2t minus 1 as t approaches infinity. If we plug in, we do get infinity over infinity. I want you to know that. But the idea is that if we are looking at the limit when the variable x, t, n, whatever it is, it approaches infinity, and you're dealing with a rational function, even if it's not a rational function, but it's a fractional function, because rational function means the top and the bottom are polynomials. They may not be polynomials. Then you must divide by highest degree term in the denominator. In this case, is t squared. We are going to divide everything by t squared. That is the technique, everyone. So I'm going to remind you what we discussed before. So to find the limit, you plug in, you get a number, you're done. You get 0 over a number, that means 0. You get a number over 0. You have to figure out if it's positive or negative infinity. And some of the indeterminate forms are 0 over 0, infinity over infinity, infinity minus infinity, and more. So the technique in this case is to divide by highest degree term in the denominator, which is t squared. So every term in the numerator, every term in the denominator, they are all divided by t squared, and we are going to simplify every term. So what happens? Since t is approaching infinity, if we replace the t with infinity, everything goes to 0 except 1. So it is extremely important to see that we are here. we have 0 over some number. That means 0 over 1, which makes it 0. That's really the key. Now, in part B, we are dealing with a rational expression. We are taking the limit as t approaches infinity. Because this is approaching infinity, we use the same technique. We divide by highest degree term in the denominator, which happened to be t. We divide everything by t. So there are 3 terms in the numerator, 2 in the denominator. Everything gets divided by t. When we do that, the next step is to simplify. So this becomes t, this is 2, this is 7 over t minus 5, 7 over t. And now there's no way to simplify it any further if you plug in. Now we're going to plug in. This is infinity, this is t, this is 2, this is 7 over infinity, which means 0. This is minus 5, this is 7 over infinity, which means 0. So it's important to know that the top is infinity plus 2 or plus 20,000 or minus 20,000 or divided by 10,000. It is still, or times 10,000. The top is infinity. And the bottom is minus 5. The key is that the bottom is negative. If it were any positive number, let's say it was 5 or 5,000 or 10 billion, the answer would be positive infinity. Because the bottom is negative, positive over negative results in negative infinity. Negative infinity. And that's the key. For part C, if you plug in, it is important to know that the square root of infinity squared plus 1 is still infinity, because infinity times any number, assuming positive, of course. If it's negative, infinity times, for example, minus 2 is minus infinity. So infinity times any positive number is infinity. If you take a square root of that, is infinity. If you take a cube root of that, is infinity. And so in this case, you square it and then you add 1 and you take a root, it is still infinity. And the bottom line is becomes infinity over infinity. And remember, the reason is indeterminate, and that requires our algebraic technique or more work, because anything can happen. When you end up with infinity minus infinity, the result could be 0, could be infinity, or could be some other number, as you will observe. So it is important to understand that you can't just assume infinity minus infinity is a specific number of your choice, such as 0. So what is the technique here? The technique is to multiply by its conjugate and divide by it. Why? Because you have a square root. Anytime you have a square root, the technique is the conjugate. So the conjugate means you change this to a plus sign, you put it at top and the bottom here. So the conjugate means you change this to a plus sign. And so what happens? The denominator remains unchanged, but the numerator you're looking at a minus b times a plus b, and the product is a squared minus b squared, which means this is going to get squared up and come out of the radical sign, minus x squared. The denominator remains. So clearly, we can drop those. We write what we have. And now, if you plug in, you get 1 over infinity plus infinity, which is still infinity. And so any number over infinity, no matter how large it is, the answer is 0. So this case ends up being 0, but that's not always the case. All right, we want to take a limit here. Of 12 over 4 plus 3 e to the power minus t as t approaches infinity. We plug in and observe. When we replace the t with infinity, e to the power of minus t becomes 0. And here's the reason. E to the power of minus infinity is 1 over e to the power of infinity, and that's why it's 0. It has got to do with negative exponential rules, and 12 over 4 equals 3. Now, if we look at part B, and if we plug in, the top goes to positive infinity when you replace it. And the bottom goes to negative infinity. And although it's not a rational function, remember, a rational function, the top and the bottom are both polynomials. This is a fractional function, I'm going to call it, because t is approaching infinity. We use the same technique. We divide the top and the bottom by highest value in the denominator, which happened to be e to the power of t. So we divide everything by e to the power of t. And we simplify. As you can see, when t goes to infinity, this goes to 0, this goes to 0. The answer is positive 1 over negative 3, or negative 1/3. The last one, if we plug in, we get infinity squared minus infinity, or in short, infinity minus infinity, which is also indeterminate. And we have to use a technique. In this case, that technique is factoring. So we factor the x out. Now we're going to replace the x with infinity. And infinity minus 1 or minus any other number is still infinity class, and infinity times infinity is, you say infinity squared is still infinity. So the point being, infinity minus infinity can go to 0, can go to infinity, can go to a different number. You have to work it out. And that's why it's called indeterminate. Indeterminate. The limit of e to the power of minus x. Ivan, did you have a question?
Yeah.
From the previous page?
Yeah, from the previous page.
Go ahead.
So in problem A, we put e to negative power of t as 0, but in problem B, we wouldn't put 0 for e to the power of t.
No. If you look at this one, this is e to the power of minus t. So that makes it e to the power of minus infinity. And we use the fact that a to the power of minus m is 1 over a to the power of m becomes 1 over e to the power of infinity, which is 0. We are dealing with we are dealing with a negative exponential. Sure. All right. So the limit of e to the power of minus x plus 2 cosine 3x as x approaches infinity. How do we deal with this? Let's cut this into two limits. Limits of the first piece plus the limit of the second piece, and number 2 comes out from the second piece, and this is what we get. Now, this actually repeats the same as the previous page. This part is really e to the power of minus infinity, which is 1 over e to the power of infinity, which is 0. The limit of e to the power of minus x as x approaches infinity becomes 0. But this part, the 2 in front or 5 or 10 makes no difference, gets multiplied by that limit. This piece, the limit of cosine or sine, when x approaches infinity, it oscillates. It does not exist. DNE does not exist, this part. So let me write this at the bottom. The limit of sine x as x approaches infinity does not exist. The limit of cosine x or 5x or 10x, that doesn't make any difference. As x approaches infinity does not exist because they both oscillate between -1 and 1. As you know, the range for sine and cosine is 1, and from -1 and 1, they oscillate. Therefore, because the second part, the limit doesn't exist, the whole thing, the limit does not exist. This one does have a limit, but this one fails. Let's look at the limit of e to the power of 3x minus e to the power of -3x over e to the power of 3x plus e to the power of minus 3x as x approaches infinity. So again, it's not a rational function. It's a fractional function. And since x approaches infinity, we are going to use the same technique, which means because this is approaching infinity, we divide by highest value term or piece in the denominator, which is e to the power of 3x. So let's divide everything by e to the power of 3x. And I want you to observe very closely here as to what happens. When you divide this one by e to the power of 3x, this gives you 1. When you divide this one by e to the power of 3x, and I'm going to write it up here because I want to make sure everybody understands why we get e to the power of minus 6x, and with the sign, whatever that one is. This one also gives you 1, and this one with the proper sign plus e to the power of minus 6x, because when you divide these two, you're looking at e to the power of minus 3x over e to the power of 3x, and that's e to the power of minus 3x, which gives you e to the power of minus 6x. Where does it come from? A to the power of m over a to the power of n is a to the power of m minus n, the quotient rule for exponentials. So by now we know if we replace it with infinity, e to the power of minus 6 times infinity, that piece goes to 0, that piece goes to 0. The answer is 1 over 1 or 1. So again, e to the power of minus infinity, this piece goes to 0, both of them. The limit of tan inverse of ln x as x approaches 0 from the right. In essence, you are interested in getting the limit, and you can interchange the tan inverse and limit. So you are going to look at this one, and I hope everybody remembers from the graph, this one is negative infinity. Why is that? Let me quickly remind you. This is the graph of y equals ln x, and therefore this shows why this is negative infinity. So tan inverse of negative infinity is negative power 2. You can do a couple of things. One is to say, what is this equal to? Let's say alpha. By definition, tan of alpha is minus infinity, and that means alpha must be minus power 2. Again, if you have a difficult time remembering this, the graph I just actually gave you, it was an, of course, 2 scale. It looks like this, almost like y equals x cubed. This is x equals minus power 2. This is x equals pi over 2, and this function is y equals tan x. And we need to know the general shape of all essential functions, elementary functions. One of them is the tan function. When we know that, then we know the answer to that is negative pi over 2. Negative pi over 2. All right, we want to move on to the next question. And so I'm going to clean up the page so we can use this. We want to find the limit of sine squared x over x squared plus 1 as x approaches infinity. And we are going to use the technique we used before to get to the answer. In this case, we remember that sine is between negative 1 and 1, and we're going to use this squeeze theorem. I'm going to remind you of the squeeze theorem. If we have g between f and h, and the limit of f and h, both of them, when x approaches a, is the same thing, namely L, the one in between, the limit of g of x as x approaches a becomes L. This is known as the squeeze theorem. So we are going to use that one. So sine is between negative 1 and 1. We want to get to this. So let's square this. And as you recall, when you square this, this becomes squared. If it's 5, becomes 25, 7 becomes 49. But if you have a negative number, you have to replace it with 0. Because if you square this, that's also 1. But what happens is that sine squared can be any number in between 0 and 1. And that's important to understand. Because sine can be 0, as you know. Therefore, sine squared can be 0. We want to make it look like this. So we have to multiply by this 1 over x squared plus 1. 1 over x squared plus 1. As you know, this is a positive expression. Because the numerator is positive, the bottom is also x squared plus 1 is positive, and therefore the inequality remains intact. When we multiply this one by the left side, it becomes the same thing, 0. When you multiply it by the middle term, we get this one. And the right side, we get 1 over x squared plus 1. In other words, it's a if you take a limit of the left side, namely 0, as x approaches infinity, obviously you get 0. If you take the limit of the right side, 1 over x squared plus 1, as x approaches infinity, obviously we get 0. We write that. So again, I hope you see that. When x approaches infinity, that becomes 0. And by the squeeze theorem, the middle piece, the limit of the middle piece as x approaches infinity must also be 0 by the squeeze theorem. And you have to mention the squeeze theorem. That is extremely important to understand why this is the case. Find asymptotes where f of x is 2x squared plus 1 over 3x squared plus 2x minus 1. And horizontal asymptotes have a definition. The limit of f of x as x approaches plus minus infinity is a limit L. That means y equals L. And the limit of f of x as x approaches a, or a from the left or a from the right, p is x equals a. So the top one, this means y equals L. Okay. So let's look at those as far as the horizontal asymptote is concerned. You take a limit, and whether it approaches infinity or negative infinity, the technique is if you're dealing with any of them, you divide by highest degree term in the denominator, namely x squared. And when we do that, so we divide by highest degree term in the denominator, which is x squared, we get two here, 3 here. This is 1 over x squared. This is plus 2 over x. This is minus 1 over x squared. So this one is 3. So the answer is 2/3. And therefore, the horizontal asymptote has the equation y equals 2/3. Now, what I want to remind you is what you had seen in algebra, pre-calculus, college algebra, regarding horizontal asymptotes and rational functions. When rational functions are given, as a x to the power of n over p x to the power of m, where the degree for the numerator is n, the degree for the denominator is m. I hope you remember that they said if n is less than m, then we're talking about the horizontal asymptote, y equals 0. If the degree of the numerator is smaller than the degree of the denominator. If n was equal to m, Then the horizontal asymptote had the equation y equals a over b. The leading coefficient of the top and the bottom take over, as it happens here. If n is larger than m, there is no horizontal asymptote. If it was precisely m plus 1, then we had oblique or slant asymptote, which meant you had to do long division, and the linear function would be the slant asymptote. So you could see that probably very fast the answer was this, but I wanted to show the details as to how you arrive at the answer. And also I wanted to remind you of what we have seen in algebra. We're going to continue, so I'm going to clean up the writing. So the next one is VA. In order to find VA and use this, basically you set the denominator equal to 0. And again, let me just, so this was 3. That's important to know. So set the denominator equal to 0 and you do the factoring. It's very simple. Number 3 is a prime number. And negative 1 is just the product of positive 1 and negative 1. We have no choice. So it becomes fairly obvious that x is either 1/3 from the first one or negative 1 from the second one. So there are 2 vertical asymptotes. We want to find a formula for a function that has a VA, x equals 1 and x equals 3. So it has 2 vertical asymptotes and HA, y equals 1, 1 horizontal asymptote. So we have 2 vertical asymptotes and 1 horizontal asymptote where y equals 1. So one possibility class would be the following. We start with if y or f of x equals fraction bar the denominator. X equals 1 gives us x minus 1. X equals 3 gives us x minus 3. And then the fact that the horizontal asymptote y equals 1, if you look at the denominator, you have x squared minus 4x plus 3. So because this is x squared, and in the numerator, if we want y to be 1, it has to have the same, so degrees 2, we need the same degree. Same degree, namely 2. So the numerator has to be x squared. Why not, for example, 5x squared? If we had, let's say, 5x squared, then y would be 5 over 1, which is 5. So we need x squared at top. Now, it could be x squared plus something else. Maybe it's x squared plus 7. Or x squared plus 3x minus 18. So this is one possibility. There are infinitely many answers. This is one possible solution.